Alright, good morning, hello and welcome. Today is day 5 of quarantine. Our goal today is to talk about the electric potential energy. We'll try to put everything together, all the force, field, and potential, and now potential energy all together into one. Good morning, Victoria. Hey, there's Giorgio. Alright, welcome. Make sure you guys subscribe to our YouTube channel. The link is down below. We're getting closer to our goal of 100 subscribers, and once we get there, we can get our own custom URL link. That'll be cool. But anyway, I'm going to start today by making this chart of equations. Now, one thing to note is that you won't have to memorize them. It does make things easier if you can memorize them, but if there was a theoretical test, these equations would be given to you. Alright, so I'm going to make a chart here. I don't like this. Let's use ink to shape. Okay, that's good enough. Here we go. Okay. Alright, so this chart, here at the top left, we're going to write down our force equation. We know that the electric force is equal to K Q1, Q2 over the distance squared. And remember, this is a magnitude, so we only do absolute value. So I'll just put absolute value for the whole thing. And then the electric field equation. So this is the force. This is the field. Electric field is KQ over R squared. So it's just single Q. Now you don't want to plug in positive and negative on this one either, so we'll put absolute value, and then you have to determine the direction on your own. Okay, use law of attraction for the force. If it's repelling, it's away. If it is attracting, it is towards. With the electric field, if it's from a plus charge, it moves away. If it's from a negative charge, it moves towards the negative charge. Okay. These are scalars. All right, scalars. Oh no, not scalars. These are vectors. Vectors. So they have magnitude and direction. Okay. This is in newtons. Newtons. This one is in newtons per coulombs. Newtons per coulombs. The next ones are scalars, these two here. Scalar means that it's just a magnitude. Without any direction, it's just a value. However, they can be plus or minus. But can be plus or minus. So the first one is, what we'll do, potential energy. Electric potential energy, PEE. And that is Q, Q2 over single R. Okay, notice how the top two have R squareds, the vectors have R squareds, the scalars just have R in the denominator. And lastly we have V, which is the potential. K single Q single R. Okay, this is called the potential energy. Potential energy. And then this one we just dropped the word energy. This is just the potential. Potential of space. Okay. Of course, energy is measured in joules. Capital J. The potential is measured in V, which is volts. Now to go from one thing to another, you can find field, or you can find force given the field, etc., using this equation. The force is equal to the charge times the electric field. And then you can kind of divide. So force divided by charge would give you the field. Okay. This one here, you can go from electric field to potential, and it works as long as our electric field is constant. So this is the VED equation. Delta V is equal to E times D. This is great when you have uniform electric field. So E is constant. E is constant. Okay. Otherwise, you have to use, calculus. If you like calculus, consider taking AP Physics C. Which is, so if you have a changing E, you have to use something called derivatives to figure things out. Alright, potential energy and potential, well, these two are related by energy, PE, is equal to the charge times potential. So it's almost like this one. Force is equal to QE. PE is equal to QV. Yeah? Alright, can you guys hear me? Is the microphone better today? I changed some settings around. I think it should be better. I don't know. Oh, it is better? Thank you. Alright, so again, you don't have to memorize all these formulas. You will be given the formulas if you were to take a test, but you should know how they work. So know how they work in that the force is a vector, the field is a vector, it has both magnitude and direction. You can't just add them up, you have to do vector components, sigma fx, sigma fy, sigma ex, sigma ey, etc. Whereas the potential energy and potential are all scalar, so you can literally just add them up. Don't have to do vector components because they're not vectors. Alright, so let's do a couple problems with potential energy, then we'll take some questions from Mastering Physics, and the last thing is to get started on our electric field worksheet that you can find at zphysics.net. Alright, so how do we use this potential energy thing? Well, there's a couple ways. Number one, let's say we have two positive charges. One is next to a wall, so it can't move. It is kind of stationary. Whereas the other positive charge is some distance away. This is Q1, Q2. We're going to let Q1 equal to Q2 equal to, do we want numbers? I guess we'll use numbers. 2 microcoulombs. That's a lot, actually. Whatever. And R is equal to, let's just do a quick 10 centimeters. Okay. So by being this far apart, there's a certain amount of electrical potential energy that is stored in the electric field. Okay? You want to imagine the electric field, the repulsion, is kind of being like a spring that you're squishing, a theoretical spring that you've squished and you loaded it up with energy. Okay, so it's like a spring in there, and when you let go, this positive charge will just fly out and move to the right. It will convert its electrical potential energy, PEE, into kinetic energy, KE. Okay, it's kind of like doing the pest to peg, and remember how we did peg magah to KE. In this case, we're doing pest to KE, etc., but it's electrical potential energy instead of spring energy. Okay. So a typical question might be, what is the velocity of Q2 at 40 centimeters? So we're 4 times the distance away. So notice how in this model, because of this wall, Q1 can't move. So all of the energy will essentially go into Q2. Okay, accelerating Q2, making it go faster, converting the electrical potential energy directly into the kinetic energy of Q2. All right. And if I wanted to know velocity, eventually I'll need to know the mass. So m is equal to, like, I'm getting nasally. M is equal to, let's see. We'll make it easy. Let's make it like, no, let's make it 2 kgs. M1 equals M2, so they're identical. Alright, so this should be enough information to solve this. Alright, we have 2 charges that are next to each other. In order for them to be next to each other, someone had to do work to push the Q2 into Q1, because naturally they'll repel each other away. So someone had to do work, and that work was converted into the electrical potential energy, and now by releasing it, we're going to get back the stored energy from electrical potential, and that will eventually convert into the kinetic energy of Q2. Okay, so what is the electrical potential energy? Well, PEE is, so this is another form of conservation of energy equation. PEE is K times Q1 times Q2 over R, and this electrical potential energy, PEE, must equal the kinetic energy of object 2. So that would be K Q2. Oops, that's not right. The kinetic energy formula is 1/2 mass number 2, velocity of number 2 squared. My dog is back. He wants to do more physics. Excellent. We should give him like a physics name. What's his name? Is it like Bolt or something like that? It should be like Bolt. Can we rename your dog? Alright, so all we're doing is trying to isolate this V. Of course, we want to eat our vegetables first. We're going to multiply by 2 and then divide by the mass. So you get 2kq over r equals mv squared. Get rid of the m and then square root. So v2 is equal to the square root of 2k q1 q2 over Mr. 2 m2r. Leonardo. Oh, he's actually Leo. That's so cool. Leo. When did you get him? Did you get him after taking physics, or did you get him before taking physics? His name is Lambda. V2, so let's see, let's go and plug and chug now. 2 times 9E9. Go and get your calculators out and plug it in. My dog's name used to be Leo, but we changed it to Buddy. Buddy? Why Buddy? Leo's such a cool name. Q1 was 2 microcoulombs, 2e negative 6, and they're both positive, so 2e negative 6 divided by the mass, which was 2 kilograms. divided by the distance. Now we have two distances. R was 10. Well, we want to find the velocity. We want to find the velocity at 40 centimeters. At 40 centimeters. Sophie is named after the girl from Hal's Moving Castle. Oh, okay. We want to find the R at 40 centimeters. Okay. So we have to take a look to the before and after picture. Before, we were 10 centimeters apart, so there's a certain amount of potential energy. And then after, they are 40 centimeters apart, and this is the final potential energy. Okay, and it is this change in energy. It is this change in energy that will convert into the kinetic energy. Kinetic energy of our object 2. Okay, so originally we had K Q1 Q2 over R1 or Ri, but we need to subtract that from our K Q1 Q2 over R final. Right, now what is this? Well, that would be the difference or the change in potential energy, and this is what's converted into our kinetic energy formula. I think I should just change all of this. I'm going to change all of this into the difference in the potential energy. So instead of writing all of that, we can write it as square root of 2 times the change in potential energy divided by the mass of number 2. Yeah, I'm not going to do this. That'll take, because I have to subtract and then find common denominators, and I don't want to find common denominators. So we'll do it slightly easier in that we'll just find the potential energy. So this orange piece here, K Q1 Q2 over R, this part, is the potential energy difference that we're looking for. So that would be 9E9, and we'll do the absolute value of it. So absolute value of 9E9 times the first charge, 2E negative 6, times the second charge, 2E negative 6, over R1. Now, over RF. RF is 4 times R1, right? So we could write it as 4I RI Was it 10 centimeters? Yeah, it was 10 centimeters, which is 0.1 meters. Minus 9E9, 2E negative 6, 2E negative 6, divided by 0.1. That's the value. So this will give us our delta PE. Okay. You can plug this in directly into your calculator or look for patterns. If I look for patterns, I can multiply the right side by 4 over 4. This will have the same denominator, which means we get 1 minus this, which is the same as -3, and if I take the absolute value, I'll get a positive. So 3 times K Q1 Q2 over 4 times R initial. Okay. Now, this is just me looking for patterns again. If you don't like looking for patterns, you can just plug this stuff into your calculator. That should give you the same answer. 9. Alright. So what do we get? Let's go and use Wolfram Alpha, maybe? Let's use Wolfram Alpha. 9E9 times Q1. Now Q1 times Q2 gives me 2 times 2 is 4, so 4 times 10 to the negative 12. 4e negative 12 divided by 0.4. 4 times 0.1 is 0.4. Man, the first one worked, but the second one didn't. Let's try that again. There we go. Alright, chat, what is the answer? It is a very small answer. Anyone doing it with us? I'm getting 0.27 joules, of course. Now, if I do it in pieces, I guess we can do it in pieces. 9e9 times 4e negative 12. 4e negative 12 divided by 0.4. 4 times 0.1 is 0.4. The first one is 0.09, right? 0.09. And then you're subtracting the next one. Next one should be something bigger. 0.36. And once you take the absolute value, we get this much energy. So this was the energy that was lost from potential energy, and this is the energy that will be turned into kinetic. Alright, so if I do my velocity now, velocity is equal to square root of 2 times the potential difference divided by the mass of the second object. So that's 2 times this 0.27. Oh no. Undo. 27 divided by the mass, and that we said the mass was 2 kg, so the 2's cancel. Oops. There we go. I'll just get rid of the units for now. 2's cancel. Square root of 0.27. And the square root of 0.27 is, I don't know, let me plug it in again. SQRT 0.27. 0.5196, so I'm going to go with 0.52. 0.52 meters per second. Okay, so what we did was we found the change in potential energy, and we said that that change will eventually turn into the kinetic energy. Okay. But it has to be the absolute value of it, because we're going to lose potential energy. When we do final minus initial, the final minus initial would give us a negative number, negative energy. But that just means that the final potential energy is less than the initial, because some of that energy converted itself into the kinetic energy. Okay. Otherwise, if you try to do it the other way, like this way, you would have to do the subtraction inside the radical. You'd have to do this inside and here. Essentially, you can also rewrite this as by finding common denominators, this would be K Q1 Q2 over 4 times Ri minus K Q1 Q2 over Ri, which is equal to 4 over 4 absolute value of that's what I got here. Boom. Absolute value of 3/4 K Q1 Q2 over Ri. So you'd have to plug this inside there, which would just complicate things. So instead, you can say that the change in potential energy is what is converted into KE. So then you would have to do PE final minus PE initial. Do that first, and then set that equal to 1/2 kx squared, 1/2 mv squared. And then solve for velocity. Okay. The other type of problem you might get is using the parallel plates setup. Imagine having a plate like this that's all negative charge, and then having another plate like this that is all positive charge. We know that we can do this by connecting it to a battery. Right, this is in your flippy book. If you connect two metal plates to a battery, the one that's connected to the flat side will become negative. The one that is connected to the top side will become positive. And this creates a nice uniform electric field inside that goes from the positive end to the negative, straight to the left. Okay. Now if I put an electron here near the negative charge, it's going to get repelled by the negative plate and then attracted at the same time by the positive plate. And basically it will feel a force to the right, and this force, of course, is equal to that uniform electric field times the charge of the electron, which is the elementary charge, E. Okay. All right. Now, based on this separation distance, if I know how far apart the plates are, D, there's another way to figure out how fast this electron will be going once it moves d amount of distance. Okay, and that's the energy equation I gave you at the bottom of the chart. This one here, PE equals QV. So the amount of potential energy I will gain, assuming that I start from 0, you can say that the potential energy is equal to the charge times V. We'll do delta. If this is delta, this is delta. The change in potential energy must be the charge times the change in the potential. This is also called voltage. The change in potential. Okay. So where do you get this voltage number? Well, that's from the battery itself. So if the battery was, I don't know, 10 volts. Okay, so the voltage of the battery is 10 volts. Then we can find out how much energy we're going to gain. So our delta PEE would be equal to the charge of the electron, which is 1.6 negative 1.6 times 10 to the negative 19 times the difference in voltage, so that's 10 volts, like so. And yes, I'm going to get an energy change that is negative. That's because when the electron moves from the negative side to the positive side, it's going to lose potential energy, and that loss in potential energy goes into the kinetic energy. So a potential difference, or the energy difference here, will be a negative value. So that's just negative 1.6 times 10 to the negative 18. Yay! Joules. All right. Using this formula, there's also another unit for energy, which typically is used in like high-speed collision physics and if you want to work at CERN where they're crashing particles into each other, instead of measuring speeds or energies in joules or speed in meters per second, we basically use this formula and measure things in something called electron volts. Okay. 1 electron volt, and the symbol is EV. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Oh, you're welcome, Giorgio. So 1 electron volt is equal to, it's basically like the charge, but instead of being coulombs, this is not the charge. This is the same amount, but in terms of joules. In terms of joules. Yeah, we're getting more viewers today. Cool. Make sure you follow us on Twitch so you can type in chat. Yeah, hit the follow button. Okay. So if you were a scientist working at CERN, CERN is a laboratory between Switzerland and France, where they have like a giant underground tunnel, and this tunnel accelerates protons and other fancy stuff. I guess protons for now. And they crash protons into each other, seeing what is inside when it explodes. But the amount of data that they get, after the explosion is so much that it'll take, 5 to 10 years to fully analyze what happened. Okay. So if you see this EV thing in your on your mastering physics or on any standardized testing that you may take, remember an EV is just another way of measuring energy. So it's kind of like converting from American dollars to British pounds or something, or pesos. Okay, so 1 EV is equal to 1.6 times 10 to the negative 19 joules. It's basically saying that if you did 1 volt difference, between your two plates, and you just multiply it by the charge. So the energy 1 EV is 1 volt separation difference in your plates times the charge of the particle. All right, so that covers all 4 elements. So we did force, we did field, we did potential yesterday, and finally potential energy. We use potential energy. The idea is that find the difference in your potential energy first, because that's the easier way to do it, and then set that equal to your kinetic energy. Okay. Or if you know that you're in between 2 plates or you have a uniform electric field, then use the PE equals the charge times the voltage. That'll give you your energy as well. All right. I'm going to do a couple questions from our Mastering Physics number 3, and then we'll be done pretty soon. I will start with one of the conceptual questions. It's called the electric field. So this is Mastering Physics. Mastering Physics. So this is called electric field vector drawing. Electric field vector drawing. Okay. And it's actually kind of, it's conceptual, but it's pretty challenging. It's kind of hard. But anyway, it gives you some charges, and it shows you the trajectory of these charges, the vectors, or it's velocity vectors. Okay. So the first one, it shows like a negative charge that has velocity vectors. It goes diagonally at first, but it starts to curve like this. And eventually it's going this way. Okay. So that's the picture that is given, and your task is to draw the electric field based on its trajectory. Draw E. Draw E. Yes? This is facts, Chapito. Alright. So recall that if you have negative charges feel a force that is opposite to the direction of the electric field. Negative charges feel a force that is opposite to the direction of the electric field. Okay. All right. So the idea is that if I were to look at this vector in pieces, you will see that the y component, the y component doesn't actually change. Okay, so these are all constants. The sigma, or whatever, Vy is constant. Okay, the only change that is happening is in the x-axis, and we can see that the x component is shrinking. It gets smaller and smaller and smaller. So if the x component, if the x velocity is slowing down, that means there is a force in the opposite direction to the velocity. So velocity is initially pointing to the left, but it gets smaller and smaller. So v is pointing to the left, but it's getting smaller and smaller. That means there's a force the other way. Okay? But electrons, or negative charges, feel forces that are opposite to the direction of the electric field. So if you know the force is to the right, then the electric field has to be left. So the answer is left. And this is part D. Oh, I don't know why I started with D. Because I had it all the way scrolled down. Whoops. Alright, this is part D. I guess we'll go backwards. Let's do C next. C has a positive charge. Positive charge. And the velocity vectors start off upwards, but it starts to curve. Okay. Again, the idea is that the the y components are all the same. The only change that is happening is in the x-axis. It seems that the x-axis, or the x velocity, is increasing to the right. Okay. So if your velocity vector is increasing to the right, that means the force vector must also be to the right. So if your velocity is continuously increasing to the right, you are accelerating. And if you're accelerating, that means that there's a force that is pushing this positive charge to the right. And positive charges go in the same direction as the electric field. Whereas negative charges are like salmon, they go up the waterfall against the grain. Positive charges feel a force in the same direction as the electric field. All right. So that means the electric field for part C is also to the right, opposite to part D. All right. Let's do B. B, okay, shows a negative charge. Negative charge. Velocity is going left but slowing down. All right. So if velocity is going left and slowing down, which way is the force? Chat, which way is the force? Velocity is left but slowing down. Which way is the force? Imagine a car going left but slowing down. Which way is the force? Or imagine you trying to run to the left, but for some reason you're going slower and slower because someone is pushing you. Which way are they pushing you? Force is right. Good job, Speed Cat. No, what? Speedy Cat. Speedy Cat. Force is to the right. Good. When force is to the right, the velocity is going to slow down if you're trying to go left. Car brakes. Yes, car brakes. All right, so force is to the right, but this is a negative charge. Which way will the electric field be? Negative charge. Think salmon. Salmon. Which way is the electric field? Well, negative charges are opposite to positive charges. So the electric field must be in the opposite direction to the force. E is to the left. Okay. Now conceptually, how does this make sense? Well, you want to imagine how we're going to create an electric field that points to the left in the first place. To get an electric field pointing to the left, you're going to need some charges. You're going to need some negative charges here, and you're going to need some positive charges here. Remember, it goes from the plus side to the minus side. So now, if you had a negative charge, and it's trying to go left, but if it goes left, notice how it crashes into or runs into negative charges. So those negative charges will repel this single negative charge, this black one here. And that's why it slows down. So when this negative charge tries to go left in the direction of the electric field, it's going to slow down because eventually it'll hit negative charges that will repel it. Okay? Or the other way to look at it is that on the right side you have all this positive charge. You're trying to go left, but the positive charge is trying to pull you back, so you slow down. Alright. And finally, A. A has positive charge that is slowing down going left. Positive charge slowing down going left. Okay, if positive charge is slowing down going left, which way is the force? Okay, it doesn't matter if it's positive or negative. The slow down is what's going to tell you which way the force is. If you're trying to go left and you're slowing down, that means there's a force to the right. Whether it's positive or negative doesn't matter. However, the direction of the electric field matters. Negative charges go against the grain, so the direction of E and F, the electric field and the force, are opposites. Positive charges go with the grain, meaning it's going to feel a force in the same direction as the electric field, so the electric field is to the right. Alright, so this was A, B, C, and D. D and C are definitely harder, but you know how it goes. That's how it is. It gets harder as you go. All right, and the last one I'm going to do is called the suspension problem. Basically, we're trying to levitate using electrostatics. Right? You saw those little toys on my desk. We use magnets to levitate. Here we're going to use the electrostatic force to levitate. Remember that little metal snowflake that I had, and I was levitating it using my Harry Potter wand? Yes? So similarly, when you have a charge, and this is problem, it says plus minus, suspending charged particles using electric fields. Okay, so this is the next mastering physics problem. This is the title of the problem. A car suspension. No, not a car suspension. Suspension meaning to suspend, which is another fancy term for being motionless. Basically static equilibrium, where all the forces kind of cancel each other, and you're just levitating in midair. Okay. So the idea is that if you have a charged particle, okay, we know that gravity will pull it down, mg, and so we need a second force, like the electric force, to push us up. And if these two can equal each other, if the electric force is equal to mg, then the net force is equal to 0. That's because sigma F is equal to the electric force minus mg, and therefore we can suspend, meaning we can set them equal to 0 if suspended. Uh-oh, my stomach is growling. I am hungry. Let's finish this so I can go eat breakfast. Alright, So in this problem it says, what must the charge, sign, and magnitude of a particle of mass 1.45 grams be for it to remain stationary when placed in a downward electric field of some value? All right. So we're looking for the charge, the magnitude, and the sign, plus or minus. First, we have to use the conceptual information, and it says there's a downward electric field. The electric field is down. So if the electric field is down, and I need a force that points up, is this a positive charge or negative charge? Electric field is down. I know gravity's going to pull me down, but I need the force, the electric force, to be up so we can cancel gravity and float in midair. Yes, very good, Speedy Cat. We need a negative charge because a negative charge will feel a force in the opposite direction to the field. And so we have found the sign of the charge. It's a negative. And now we're going to use the sigma equation to solve for the actual value. So we know that the electric field, electric force has to equal mg. Okay. All right. There are ways to find the force. Two ways to find the force, actually. And if I look at my chart, remember the chart will be given to you, so you don't have to. Yes, you have kqq over r squared, but that equation is only good if you're trying to find the force between two charges. The other equation is this one up here, the secret one. And that's based on the electric field. The force is equal to the charge times the field. So we're going to use that one because we have the field value. So that means Q times E must equal M times G. All right? So the charge is just mass times gravity divided by the electric field. Okay? And I believe everything is given. The mass is given. Make sure you convert the mass into kg. Convert mass to kg. There we go. Gravity, what is g? What is g? What's the constant near the surface? Actually, they tell you. They're telling you to use 9.81. So use g is equal to 9.81 meters per second squared. So they're telling you to use 3 sig figs for gravity and not just 2. But gravity is a constant, so as long as you're near the surface of the Earth. Alright, that's it for the Mastering Physics help. Make sure you work on this Mastering Physics assignment. It is due on Monday. If you run into problems, we can take questions on Monday's stream. Alright. For the rest of the time, you should download the electric field worksheet. So download e-field worksheet. Download e-field worksheet. So this is very similar to the force worksheet that we worked on in class. Remember how we separated into groups and we were teaching the class, etc. I just got it wrong. What? How did you convert? So you should have mass in kilograms. Remember, there's 1,000 grams in a kilogram, so you have to divide by 1,000. Gravity is 9.81, and then divided by 660. And make sure it's a negative charge, so yeah, make sure M is in kg, not grams. What's your mass? Is it 1.45 grams? Aha. It should work. So mass times gravity divided by electric field, that should give you your charge. Alright, download the e-field worksheet, work on that. And then if you have questions, you can always email me. So that's it for the stream. Thank you for tuning in. Make sure you follow and subscribe to our YouTube channel. I'll see you next time.